we're dealing with a ring of charge. So the blue circle is a circular ring that I have turned on its side. So if we were looking down the x-axis, turn it on its side, this is the z-axis, and our ring is now turned a little bit to the side. Does that make sense? Are we good, Andrew? All right. Now, this page, and let's say that this piece right here, and actually, no, let's make the piece right here on the top for our analysis. This is our dq. And that suggests that we are interested in, say, the electric field over here at point P, a distance z from the center of the circle. This is all the setup we talked about before. This green line is going to be r, and my circle still has radius capital R. So there will be a contribution to the electric field in this direction from dq. Is that all good? Well, I didn't draw it particularly well in line. I could have done better. Can you all see, though, that there's a certain amount of symmetry here? Meaning that there's probably a piece of charge here that would do the same thing. Does that symmetry extend everywhere on the ring? Like there's a piece here and a comparable piece over there that would do the same thing. And a piece here and a comparable piece over here that would do the same thing. Just because it's in 3 dimensions doesn't change the fact that for every contribution to the electric field, there is another one that cancels off any electric field that's not along z. So they might be along x or y, but for every part that's in x, y in one direction, there's another part that's in x and y in the opposite direction. Those will all cancel out. So all I care about are the contributions to the electric field that are this way. All the E's that are in the z direction. So do you see the symmetry there? Because that's important. And like I said, so I'm only going to care about the ones that are in this direction. I'm not going to use theta, though. I'm going to use phi, because theta's already been given away to the circle, so I'm going to use phi to describe this angle. And I know that phi and that phi are the same. Pretty sure I want the cosine component. You guys see why? It's the one that's along the z-axis. So I think E along the z-axis is to the total value of E, and that ratio is cosine phi. Now, truthfully, I should put D's here to indicate that these are just the partial electric fields. Okay, so let's put all the pieces together now. So we want the whole electric field that's in the z direction. Do that. We solve this, make this dE in the z direction equals dE cosine phi. Now, based on where phi is, we're probably going to use not the actual, we're going to use the side lengths, and we'll use this side as the hypotenuse and this side as the adjacent. And that's going to give us dE c z over r. Now, the integration of that should give us the entire electric field in the z direction. So let's now look at what dE is going to be. Well, that's going to be dq times k over r squared. Well, not a problem. Now we already have dq from earlier, but dq is going to be q d theta over 2 pi. Remember, the theta represents the angle that this r vector kind of wraps around. So we just got to remember that it deals with something else, and we'll look back at that in just a minute. And lastly, probably r, remember that's going to be coming from this triangle that's right here, is going to be the root of z squared plus r squared. So I think those are all the pieces. So now let's put all those pieces together here. So dE in the z direction equals, let's start with a q d theta over 2 pi, that's the dq, times k times 1 over r squared, which is z squared plus r squared, not squared, there's r squared, times z over r, which is z over z squared plus r squared to the 1/2. There we go. So I think that's all the pieces. Yeah, looks good. So now that we're here, if I want the whole electric field, I need to integrate over the whole field, which means integrating over all of d theta. But before I do all of that, let's just kind of pull all the constants together and put them in one place. So q is a constant, k is a constant, z is a constant. Okay, that's all the top parts. And then 2 pi is a constant, and z squared plus r squared to the 3/2, all constants, times d theta. There we go. Now, integrate. And what are we going to integrate? Back here, we're going to take this from 0 to 2 pi. Well, that means E in the z direction, which is the total electric field, equals q k z over 2 pi times pi. So now the 2 pi's cancel, and we get, as our final electric field, E in the z direction, q k z over z squared plus r squared to the 3/2, which ends up being exactly the same as our 2-point charges. The only reason it's not a 2q here is because with our 2-point charges, we had 2-point charges, each of charge q. But in this case, our entire ring was charge q. But it still behaves the same way. And that's why the electric field ends up being the same. Then I would just draw a circle, or I think z-axis, right? We said z-axis. And this is the z-axis coming at us, right? So it is a ring of charge. But let's just have a little bit of geometry while we're looking at the ring from our vantage point above the ring. Is that okay? The ring has, say, we need to have some characteristic stuff. So I don't think it's too big a deal to say the ring has a radius of r, and say the entire thing has a charge of q. Okay, so back to work on this. The ring of charge has charge q and radius r. So if I were to remind you, one of the things that you're supposed to do here is recognize that there's probably some symmetry involved in this problem. But let's consider that we're going to be taking a piece of the whole ring, like just a bit of it, and that piece has charge dq. Is that okay so far? Let's work this portion of the problem for just a minute before we go to the weird perspective problem and say a few things about this that, like, I don't know, if I wanted to, I can pick a single point on the ring and have that be 0 for the length of my ring. Because remember, the whole thing is we're going to have to add up all the parts of the charge. So I need a place to start my measurement from. And let's say that from there to here is an angle theta. In that way, the portion of my charge begins here and ends there. So my my piece of ring has length ds. That okay? We've done this before, so I'm just reiterating. So I would say that the length of this piece is ds. Because I want to also remind you that dq is to ds as q is to 2 pi r. Right? If it's a uniform charge density, then the total charge is to the total length as the piece of charge is to the piece of length. That all okay? But I'm probably going to refer to my piece of charge by its location, not just its length. So to do so, I will rewrite this as r d theta. And that way, I think it'll be easier to find every piece of charge by summing up over every angle, starting at 0 and ending at 2 pi. Does that make sense? I need to have something to which I can integrate. So I know I'm going to need this in the future, but I think we've worked out what we are for our piece of charge. The r's cancel here. You guys see that, right? So this part should not surprise you though. If I was to integrate this from 0 to 2 pi, those of you who have had a run of calculus realize that the result of this will be just q, right? Do you see that? That if I add up every piece of charge over the whole ring, I get charge q, which is the charge on the ring. You should expect that, right? Because you're adding up every piece of charge for a ring whose total charge is q. So I would expect if I added this up, I would get that value back. I'm not going to take this integral. I don't need that. I'm pointing it out to those of you who can do that in your head, the calculus part of this. But what I do want is recognition that this will be something I could use for my dq in the future. All right, hold on to that. Let's go back. It's hard to see it here, but if this is where point P is, if there's an electric field in this direction from this piece, then there's a piece over here pushing it back that way, right? The XY plane is what's pictured here. Back at this picture. Well, what we're going to integrate is going to be the angle from here all the way around to here. This is adding up every contribution to the charge. So when we